Okay, this lecture is partial derivatives, and we're going to do it in three parts. First, a simple example, then we're going to look at some pictures, and finally the definition of what a partial derivative is. So here's the example. Z is a function of x and y, the two independent variables, and here we have the function. And the partial is the partial of f with respect to y, and sometimes physicists like to write this as f with a subscript of the independent variable. In this case, I'm going to do y. So if we're taking the partial with respect to y, that means we're going to treat x as a constant. So this is really pretty easy to do. Y is the variable, so we have 2 times 7 or 14. X is a constant, and then we have y plus, well, the derivative of the sine is the cosine of x plus 2y. All right, times the derivative of the inside function. Remember, the variable is y, so this is a constant. Derivative is 0. So the derivative of 2y is just 2. So we'll put the 2 there. Plus, again, with respect to y, x is a constant. The derivative of a constant is 0. So we'll just put a 0 there. Now, if we wanted to do the partial of f with respect to x, well, this time, x is the variable, and y is constant. So we have 7y squared plus derivative of the sine is cosine. Okay, the variable is x, so the derivative here is just 1. Okay, plus the derivative of the natural log of x is, of course, 1 over x. And that's all there is to it. So now let's look at some pictures. Okay, so we're talking about three-dimensional space. So what I'm going to do is draw a picture. X, y, and z is a function of x and y. And at the same time, I'm going to draw a function z is a function of just x. So I'm just going to let x vary, keeping y constant. Constant. Okay? So let's take a common function. The function is x squared plus y squared. We know this is a paraboloid. So it looks something like that. It goes on forever. And remember, we're trying to figure out the partial of f with respect to, let's say, x. So that means we're going to pick y as a constant. We can pick any constant that we want. So let's just pick, say, y is equal to 2. And we're going to let x vary from minus infinity to infinity. Z vary from minus infinity to infinity. So y equals 2 is a plane. It's a plane that comes out of the board. And if we intersect the plane with the surface, I think you can see you're going to get a curve. Okay? Now we're trying to figure out the partial of f, which is the same as z, with respect to x, keeping y a constant. And in our case, y is equal to 2. So what does this curve look like? Well, if y is 2, then our function here is z. Z is equal to x squared plus, well, 2 squared, which is 4. Okay, what's the graph of that look like? Well, 1, 2, 3, 4, and it's just a parabola. So it looks like that. So what is the partial of f with respect to x? Well, we know from the previous discussion it's 2x, but you see that that's the same as the derivative of z. The derivative of z with respect to x. And that, of course, is 2x. So the idea is take the surface, slice it with respect to one of the variables, look at the curve, and just take the derivative. And that's all there is to it. Okay, now finally, the definition of a partial derivative, right, f with respect to x, is the limit of the difference of the functions. So we have, the function f at, say, x, y, and then the function, if the independent variable that we care about is x, we're gonna let x change by a little bit. So instead of writing x, we'll write x plus a little bit, h, comma, and we're letting y be like it's a constant, it's not changing. So this is the difference, so it's how much the function changes, the surface changes when you change h a little bit, and we're going to, of course, divide that by h and take the limit as h goes to 0. So let's take our function we used before, x squared plus y squared. The partial of f with respect to x is, by definition, the limit as h goes to 0. Now, what's the function when x changes a little bit? Well, instead of x, we're going to have x plus h squared plus y squared minus the original function, which is x squared plus y squared, and then the whole thing divided by h. Divided by h. So, limit h goes to 0, and this is just a little bit of algebra. We have x squared plus 2xh plus h squared plus y squared minus x squared minus y squared, the whole thing divided by h. Okay? And now, just like in single variable calculus, things are going to, cancel out. X squared, y squared, and what's left is this term divided by h. So we have limit h tends to 0, and we're going to factor out an h, and we're left with 2x plus h. Okay, the rest goes away, except we're going to divide by h. Now, what is h divided by h? Well, they cancel as long as h is not equal to 0. If we're equal to 0, it would be undefined. So we can't let it be equal to 0. But it's not equal to 0 because h only approaches 0. Therefore, we're allowed to cancel it. So what's left? The limit as h goes to 0 of 2x. Well, 2x doesn't care about h. So that limit is just 2x. And then we have the limit as h goes to 0 of h. Well, that just goes to 0. 2x plus 0 is 2x. So there's your answer. And that's the same answer that we had earlier. I think we did it earlier. If not, we'll just do it right now. The partial of f with respect to x is 2x. Okay, it's very important to understand this process, this technique, because we're going to need similar thinking along these lines in order to do the more advanced theorems in vector calculus. Some of the fundamental theorems, we're going to need this logic. So that concludes this lecture. Thank you very much.